So hello to everybody. It's really nice to be here. I'm very happy to have joined this beautiful summer school, even if only for the second week. I can feel with you that your heads start to be a little bit full after 1.5 weeks. So I hope there's still a little bit of space to add something. As Frederick said, my name is Anke LINDNER. I am also from the ESPCI. And I will talk about something today which is very much linked to flow and fluids. I have the impression you've heard a lot about viscoelasticity, but mostly coming from the more solid-like part. So in my case, we will be really concerned with things that are very liquid-like, like water. And I mean, we've all done this a lot over the last days to pour some water. But what we will do, we will not just use the flow of a simple fluid like water, but we will add a tiny amount of polymers. So this is also something that might be different from the first lectures you have had, that I will mostly deal with dilute systems. So we'll add a tiny part of polymers, and then we will see how the flow properties of these liquids are changed. And to convince you that even in the situation of a simple fluid as water, when we add a little bit of polymer, very interesting things can happen. I have actually 2 examples here, and I will try to show you 2 films to see what happens in these situations. So all the films that you will see here are actually from Gareth McKinley's group at MIT, and they're all polymer solutions, maybe not fully dilute as I pretended, and you will see what happens, maybe. Okay, so here they will actually take a little bit of this solution, and they will put it around a roll, and they will just spin. So what you can see, despite the fact that this is a fluid, you can actually roll it up like it would be a string of some kind of material, due to the strong resistance actually of the fluid. And what you will see when it stops, it is indeed a fluid. As soon as you stop, it will flow down. Okay? And so it just continues. This is a situation that I guess most of you have seen at home. This is what is called rod climbing. You plunge a rod into a liquid, you rotate, and when you do that, you can see that the liquid will actually climb up the rod. So this is, let me just stop that here. So this is not what should happen. So if you put a rod in a simple fluid and you rotate the rod, you have centrifugal forces that would put the fluid outwards, and you should actually have a dip in your surface. So what happens here is the contrary. So the fluid moves up. So you can see that at home if you beat egg white, for example, or if you bake a cake, often the battery moves up the rod. And the last situation is a little bit comparable to the first that you saw. So what they do here is that they actually start filling a syringe. The syringe in the beginning is in contact with the fluid below, but then they actually take the syringe out of the fluid, and despite the fact that the syringe is not touching the fluid anymore, they are able to fully fill the syringe. Okay. No, I mean, I could have done the experiment in real life, but I didn't bring anything, but it works. No, there's no trick. It's not in reverse mode. I can guarantee you. But it's true, nowadays we are skeptical with everything we see. Okay. So what you can see immediately, I think, from these films, is that these fluids can have quite spectacular properties that are actually due to stresses that develop in these fluids. And in this lecture, we will try to understand what kind of properties these are and how these properties will actually influence the flow of these viscoelastic fluids. And to be a bit more precise, so what I will really be concerned with is actually what happens on the microscopic level. So here I was talking about polymers, and I will mostly talking about polymers, but it can actually be seen as a bit more general point of view. If I put microscopic particles in a flow, and then the flow will interact with these particles. And the flow will deform the particle, change their orientation, and maybe also change the transport of these particles through the flow. So everything I will discuss will be inherently non-linear. So you've heard a lot about linear rheology, about small deformations. Here is actually a fluid that will be flowing. There will be always strong deformation, and everything we will be doing, or mostly everything we'll be doing, is a strongly non-linear effect. So if we look what happens at the microscopic scale, I take a microscopic object, I put it in interaction with the flow, it will be deformed by the flow. But while it's deformed by the flow, it will also exert a stress on the flow due to this deformation. And this stress exerted by the individual particle will actually have a signature on the macroscopic flow properties. So in my picture, I will always consider like isolated particles. So it's not interaction between particles that are important, but it's the individual interaction of the particle with the flow. And then, of course, we sum up by putting several of them. And we will try also to establish the link between the two. Okay? And so why would we even bother looking at these type of polymer solutions in the relatively dilute limit? Because actually there's many situations where they're important. So first of all, in many biological fluids, we have polymer solutions. So here this is a dog that actually shreds his saliva. So you can do simpler things by maybe not right now, but just taking a little bit of saliva between two fingertips and open your fingertips, and you will see something quite stable will form by your saliva. Also, the addition of small amounts of polymer has been shown to drastically reduce the drag. So if you have a turbulent flow, you add a little bit of polymer solution, actually viscous friction is strongly reduced. And the story once that actually New York fire department uses the small addition of polymers to actually make the water jet go much faster. Or in flow in pipelines, for example. A field that has been for a long time a very intense field of research of polymer physicists was enhanced oil recovery. It's not really the direction we want to go nowadays when we talk about energy, but also in these situations a lot of additions of polymers have been used, and there's many other situations. So I tried also to make an outline of my talk. I'm relatively confident about the first part, and we'll see about the second. So my first part is really about rheology. You've heard a lot about rheology, but it's not exactly the same type of rheology that we'll be talking about. So to do this, I will first introduce, which is from my point of view, a simple or a complex fluid, which you can also call Newtonian and non-Newtonian, it's equivalent. Then I will introduce the basic non-Newtonian properties of these fluids. I will talk a little bit about classical rheology. I had a very nice introduction this morning already by Vlasis, so I can actually refer to many things he has said. Then I will cite some examples and well, end with a little bit of less classical rheology. And the second part is also, like Ken said, under construction. So at the second part, I really want to talk about flow. First, we will characterize the fluid, but then we really want to understand what these different properties mean on the flow of a fluid. And I will mainly talk about microfluidics to do that. So I will give an introduction, talk about some microfluidic rheometers, and actually we will see about the rest, how we go along. So let me first introduce what you've heard quite a lot of times already now, what is considered as a Newtonian shear viscosity. And now here we talk about simple fluids. So simple fluids are, for example, water, oil, alcohol, most of the solvents that you can use. And the definition of the viscosity, you've seen this several times. So in the beginning, the first definition of the shear viscosity was given by Newton. So it's this very simple idea. You have a fluid between two plates. You apply a force on the upper plate, and the plate will actually displace with a certain velocity. And then what you do is that you actually link the stress that you apply to the upper plate to the velocity gradient. So it's really in comparison to an elastic solid where you apply a certain stress and you will strain the material up to a certain point. Here it's really the strain rate that is important. So it's always the velocity with which I will deform. So this is actually characterized by the shear rate, also mentioned this morning and in lectures before. Just I wanted to point out so that the shear rate is a velocity gradient. So if you look at the velocity profile between the two plates, it's actually a linear profile. It's zero velocity at the bottom plate that doesn't move. It has the velocity of the upper plate, which is equivalent to the velocity of the plate. And in between it's linear. So you have a velocity gradient. That means that the velocity changes, in this case, in a constant way, linearly, with distance. But you can also see this as a strain rate. It's also the rate with which you continue straining your fluid. Okay, so these two notions are equivalent, and often when you want to compare like a simple viscous fluid with a simple elastic deformation, it's actually nice to think about deformation rates because one is just a derivative of the other. So what is important to note that in the simple picture, the viscosity is a constant. It's isotropic, it's only one constant and depends on nothing, well, maybe on the temperature, but not on the flow properties. So also what is important to note, which I think is relatively clear also, is that for the viscosity to manifest itself, you need this velocity gradient, because viscosity is a viscous dissipation process. So you need fluid layers to slide past each other to create this viscous friction. Okay? And this comes also from the fact that actually viscosity comes or introduces surface forces. So if you've heard that already also with Frédéric, that actually all these intermolecular forces are actually short-ranged forces. So if you want to create any forces or dissipation in the fluid, it will always be surface forces. So with this being said, I actually wanted to introduce classical rheology. I mean, this has been beautifully done this morning already. So let me just add some small comments to that. So first of all, I think that has also been said this morning. If possible, we would like to be as much as possible in the situation of the simple shear. So really the situation where I have one plate that moves and they create this linear velocity profile. And this has been said this morning already. I mean, it's an extremely simple situation, but experimentally, it's very hard to create. It's very hard to have two parallel plates that will displace by each other and even over a long distance. So the most direct modification of this is actually you take the two plates and instead of letting them slide like that, you bend them slightly and you will rotate one of them. So this is the quet geometry, okay? But in general, in all cases, and that has been said, you go typically to a remeter with rotating geometries, and we had this morning, it can be stress controlled or strain controlled. So if you have a geometry that rotates, you need to link two things. You need to link your rotation rate with the shear rate, and you need to link the torque that you apply on the rotating part to the stress in the system. And I actually chose only one geometry, and we are very much aligned actually with Vlasis about which geometry we want to talk about, which is the cone plate. And this has been pointed out already. What is really great about the cone plate geometry is that you manage to have a geometry where the shear rate is indeed constant everywhere in the system, which means indeed that you create this linear velocity profile. And the trick to do this here is that actually if you look about the velocity, so basically flow goes in the plane here, right? So the shear that you need to imagine is actually flow in the plane of this plate, and it's sheared on the height of the gap. So the nice thing is that if you move outwards, your velocity of rotation increases linearly with the radius, but at the same time, your gap also increases linearly with the radius. So if we go back to this very simple idea about what a shear rate is, so the shear rate, remember, is the derivative of the velocity by the distance, but if you have a linear velocity profile, it's nothing else than the velocity divided by the distance between the two plates. So this is actually the reason why when we go to this cone plate geometry, that you will have the velocity, which is omega r, divided by the radius, and I already wrote the approximation of the small angle, which corresponds to the gap height. Okay, so what this is really nice about this geometry. The only drawback might be if you have something like a suspension, a granular suspension, or something that is a little bit thicker, you have a problem with the part here, which is actually the point of the cone, and the point of the cone should, if you prolongate this, touch the bottom surface, but of course experimentally it cannot touch the bottom surface because we don't want the friction there, so you truncate it slightly, but this can be very, very tiny, I don't know, some 50 micrometers or less. So you can have systems where it's actually difficult to use that. And then we have seen this calculation already this morning. What I wanted to point out is that actually it's always the same. You always link the rotation rate to the shear rate. You always link the torque to the stress. But what is in between comes from the geometry you use. So depending on the fluid you want to measure or the system you want to work with, you can actually play with the geometry. So Vlasis asked this morning, how can I even go to a shear rate of 1000? Well, actually, it's true. It's not so easy on the remeter because you need to rotate really, really quickly. But if you make your angle very small, with the same rotation rate, you can reach higher shear rates. And the same applies for the relation between the torque and the stress, which is written here. So if you want to have a relatively high torque, but you work with water, which is not very viscous, for example, you can just play on your radius. So if you make your geometry bigger, your torque will be bigger for the same type of fluid. So this is why the choice of the geometry, in addition with the specific properties of your meter can be actually very important. Okay, so this was, oh, sorry, yes. Yeah, yeah, I realized that. Yeah, it's true. I actually drew it like this, which would be if you actually cut out the part. As long as you're talking about viscosity, I think is not so important. I will talk about normal stresses a bit later, and actually on the normal stress transparency, I have drawn it the other way around because there the boundary conditions are extremely important. I agree. But it really depends also. If you have something very liquid-like, it's actually impossible not to have the interface like this. If I have water in a complete geometry and I have a small gap, I guess it will often look like that. Yeah, but it's a very good remark. I realized this also this morning. Demo. Okay, so now we know two things. We know the very simple definition of Newton about the viscosity, linking stress to shear rate, but in a very simple situation. Only if I have actually this linear velocity profile, I have some ideas how to measure that. But if I think about flow in general, that's not very satisfying because flow is normally much more complex than that. So what we really would like to have is something a bit more general that will link stresses to shear rates in a more general situation. And this can actually be done for a simple fluid quite easily, and I'm just skipping many steps and writing here directly what we call a constitutive equation. So this constitutive equation is nothing else in the end than Newton's law. It's just generalized in a way that I actually have a stress tensor which describes stresses in all directions in the volume of the fluid. And I have a tensor here that we have also seen this morning, which is actually the velocity gradient tensor. And in between, I have the viscosity. So the way I write things, I actually define my velocity gradient tensor to be symmetric, as you've already seen. So this is for everybody the same, but I actually define it with a 1/2. And actually this 1/2 brings the 2 in the constitutive equation. Okay, so why do we define the shear rate tensor in the fact that it's actually symmetric? If you take just some general type of flow, you would construct a matrix which is just dvi by dx, which is just the gradients everywhere. And then you know that every matrix you can actually split it up just by construction into a symmetric and into an antisymmetric part. And if you look a bit closer what the antisymmetric part corresponds to, it turns out that the antisymmetric part corresponds to a solid body rotation. In a solid body rotation, no slices of fluids are sliding past each other. So a solid body rotation does not, the viscosity does not manifest itself in a solid body rotation. So this is why actually when we talk about viscosity and the viscous stress tensor, the only part we use is the symmetric part. And that's why so far you've always seen the symmetric part. But keep in mind, there's more to the flow, and what is more to the flow is the asymmetric part that corresponds to a rotation that for some situations can become important. So this, I think, has been nicely introduced already. So I just draw even more simple. So if you go, I don't know, from Herbert Hoy to Vlasis to me, it gets more and more simple. I just drew one face of the stress tensor. So just to remind, the stress tensor is actually there to give us forces on arbitrary surface elements. So if I have the stress tensor, I can say I want to have this small surface element, and from this I can always get the force that is applied to this surface element. And what is important to note for the following, that there's two types of stresses. There's shear stresses and there's normal stresses. So far, when I talked about the two plates, this clearly is a situation with a shear stress. So I'm shearing along this direction. And when Frédéric talked about the surface tension, he talked a lot about pressure. So pressure naturally is a normal stress. Right. Excuse me, what is special? Yeah, okay, sorry. So in this case, the stress tensor, I wrote only the viscous stress tensor, so I didn't write the pressure. So if you want to have the full stress tensor, you would add on the diagonal elements the pressure. Okay. That depends on the flow. So for a simple shear, and I will show this right afterwards, for a simple shear, it's, well, it's always traceless for, okay, let me take that again. For a simple shear, you will have no elements on the diagonal because all elements you have, that is flow in one direction, the gradient in the other direction. But if you have another type of flow, and I will show you some of them, then you can have elements on the diagonal. However, if you are incompressible and we are working with fluids, so in fluids everything is incompressible, the sum of your diagonal elements, so your trace, will always be 0. Okay? Okay, so I also wanted to insist on the fact that having a constitutive equation is something actually very marvelous. If you have a constitutive equation, you can link any kind of stress distribution to a shear gradient distribution, or any shear gradient distribution to a stress distribution. So it's really something very general that allows you to fully describe kind of any kind of situation. This is not at all the case if you have a non-Newtonian fluid, as we will see a little bit later. And just before we go there, I wanted to quickly convince you that actually what I wrote here is exactly the same thing than what we had on the first slide with the Newton's viscosity. And this is maybe what you asked for. So if I write a simple shear flow, I have only a component into the x direction. It only varies into the y direction. So if I write my E tensor by construction, you will see that I just end up with 1/2 of the shear rate here and 1/2 of the shear rate here. So I made it symmetric, okay? And then I just use the constitutive equation, and if I use the constitutive equation, I end up with these eta gamma dot and eta gamma dot on these two elements. And this is actually the same thing as we wrote for Newton's law. It's just now we know that to be a little bit more precise in the Newton's law, it's sigma xy, which is the stress that actually plays a role. Okay, so this was to describe the field of a simple fluid, but of course we're not here to talk about simple fluids. So I have a very full transparency, I'm sorry about that, about many examples for complex fluids. And I'm really sorry, Fred, I think it's the only time I will show an emulsion in my whole talk. So this is actually a slide to give you an idea of the world of complex fluids, because actually there's many of them. I think you're not surprised after 1.5 weeks in Cargese, but sometimes from people who live in the world of hydrodynamics, they're a little bit surprised to realize that actually water is actually one of the rare fluids which are Newtonian, and most of all the other things are non-Newtonian. So what is actually really nice about this field is that these fluids occur in very different situations. So many of them occur in biology. If you think about the flow of blood, so you have these red blood cells and they can actually aggregate and form what is called a rouleau. If you put them under flow, they would align with the flow and actually lead to complex properties. We already talked about saliva. So saliva has this resistance to extension, which comes actually from polymers that are in the saliva. And there's many more biological fluids that you could cite. There's many applications in food and cosmetics. And we already talked about food, I think mostly in the general lecture yesterday evening. So I think this is my own emulsion. If you look about mayonnaise, it's actually an emulsion of oil and lemon juice. Chocolate mousse is actually air bubbles in the surrounding matrix. We already saw foam of beer. And you can also have things like yogurt. You realize that sometimes the yogurt, when you open just your yogurt, it's quite solid-like. When you start to stir it, it gets very easily fluidized. It can actually be due to the addition of a certain type of polymers, but also just by the network polymers that are already present in the yogurt. Quite similar things happen for cosmetics. If you think about toothpaste, so these are things that have something that one calls a yield stress that I will not talk about later on, but it's very widespread in cosmetics and also in the food industry. It's something that allows you, when you apply a certain stress above a critical stress, to make things flow. Just a second, to make things flow. However, once you extrude things from your tube, they will actually stay and are able to sustain their own weight. Yeah. I will come to that. I'm trying to bring you to my explanation of what for me is a complex fluid. So bear with me a little longer. And actually both in cosmetics and in food, it turns out that people are very receptive to texture. So a chocolate mousse is not only good because it has good chocolate, but people are very receptive to the way it actually behaves in your mouth. And it's very similar to cosmetics. So apparently it's very important how the cream feels when you put it on your arm, and not only how beneficial it is for other types. Then I just cited some examples from geology. You can also have like a flow of muds or lava, and of course building materials. We've heard about cement or paint already. So many of these properties I will not be able to talk about, but all these complex fluids have actually specific properties designed for their application. And what I find really nice in the field of rheology, that you can do the same type of experiment and understand something in biology or understand something in a building material. So it's actually very widespread. But for the purpose of today, what I want you to realize, if you look at all of these systems, there's always, and I think that's what you've been pointing at, there's always some kind of a mesoscopic structure. So if I think about blood, I actually have a fluid which is more or less Newtonian-like, and I add the red blood cells. If I think about these emulsions or the cosmetics, there's often polymers, which are also a mesoscopic structure. We've seen, depending on what type of polymer it is, it can be between 10 nanometers and maybe up to a micron. Or I can have bubbles, or I can have particles in there. So all these fluids are made by a simple fluid, and I added something to the fluid. And so why is this the most important ingredient to create a complex fluid? So let us go back once to what is a simple fluid. So if you think about a simple Newtonian fluid, maybe again water, and it has a molecular structure, and I look at the typical time scales that appear in this fluid. So what we saw this morning, we had the typical time scale of a colloid of 1 micron. If I look about the time it takes to move over the distance of the colloid, I think it was around a second. So here we are on the molecular scale, and this depends, I think, on r to the power 3. So I get very, 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 very small time scales. So typically 10 to the minus 9, it probably depends what exactly you input there, is a typical time scale for thermal fluctuations. So now if you think about it, so you want to do some kind of deformation to your system. So whatever you try to do to the system, the thermal fluctuations will be so fast that they will recalibrate the system much faster than you can actually deform or shear the system. So a Newtonian or a simple fluid is actually a fluid where what I do to the system will not change the internal structure. And in this case, I only need one parameter to describe the system. I only need the viscosity, and I know that my constitutive equation remains valid. Yeah. Yes. Yes. If you would be able to go faster than this internal timescale, then it would be non-Newtonian also. Yeah. And so now if you think about the non-Newtonian fluids that we saw, so all of them have a mesoscopic structure with sizes that are actually much bigger. So these structures can be typically polymers, if you've heard a lot about, but they can also be fibers, some kind of elongated small rods. They can be bubbles. And now if you actually apply a flow to these structures, the polymer can be extended, the fiber can be reoriented, or can maybe have a buckling instability, the bubble can be deformed. So the flow will actually create a deformation of the object. And typical timescales of this, so they can vary a lot because it really depends on what you're looking at, but typical timescales can easily go from 10 to the minus 3 to 100 seconds. So it can be a timescale for relaxation, for reorientation, etc. And now you can actually realize that if you make a shear flow, if you deform your fluid, that you will be able to change the internal structure of your fluid. And so you will change the properties of the fluid by applying the stress. So you can also see from here already that clearly you're in a nonlinear situation. You have a flow that you will apply, will change the structure, the internal structure of the fluid. But of course, once you've changed the internal structure of the fluid, they will also change the flow properties. Okay. So it's really this interaction that creates all the interesting effects in complex fluids. Yeah. So you mean the timescale of the mesoscopic structure? Yeah, I think Vlasta has also said it quite nicely this morning. It can be whatever is the relevant timescale of your system. So if you have a polymer, it can be the Zim relaxation time, or it can be a different relaxation time. Oh, so yeah, so it comes from the interaction of the object with the flow, but and it will be linked to the flow. So if you stretch a polymer in a very viscous fluid, it will take longer for the polymer to come back. So it's already dependent on the solvent that you put it in. And if you have a fiber, you can imagine you buckle your fiber and you let it relax. or you look at Brownian motion to equilibrator orientations. So it can come from very different situations, and I actually will talk about two a bit later on. But the very important thing, and that has been introduced also this morning, is really that if I talk about non-Newtonian fluids, I always need to consider the timescale, because the remark was very correct. If I could shear the water fast enough, it would also be a non-Newtonian fluid. And this brings up the Weissenberg number that we discussed already this morning. So I really need to compare the relaxation time of my system, choosing the good one, the relevant one, with a relevant flow timescale. And the shear rate is actually the inverse of a time. So it's the relevant timescale of your flow. But that also means a non-Newtonian fluid is never just by definition a non-Newtonian fluid, but I always need to consider actually these relation of timescales, and it will behave as a non-Newtonian fluid only if I overcome a certain Weissenberg number. Typically we say it needs to be larger than 1. And so this actually brings us to a situation which is much more complicated. So, well, I already said that. Now, in this structure, I can imagine that first of all, my properties, I expect them to be non-Newtonian. So, for example, to depend on the shear rate. I expect these properties to be non-linear, for example, to depend on the shear rate. They can also be anisotropic. If you imagine a fiber oriented in different directions, the polymer stretched. So this also makes things more complicated, and we understand naturally that one parameter like the viscosity will probably not be enough. So we are now in a situation, we are quite sure that the constitutive equation doesn't work anymore. We might have many parameters that we need to characterize. So we are in a situation that is much more complicated. But as we are actually rheologists, we want to try to make our life a little bit more easy and to actually live with this situation. Rheologists have created something that they call rheological flow. So we don't want to be as fully comprehensive as with the constitutive equation. We don't want to start with the idea that we can describe any kind of flow, but we want to start with the idea to have some well-defined flows and to see what we can do in these flows. And so these are these famous rheological flows. I think the first one you've guessed. The first one is the simple shear. I think you start to know that by now. But then there's another one, and it has actually been touched on by the last lectures. So yesterday you had these fiber stretching apparatus. So if you have these fiber stretching, what you actually do is an elongation to your fluid. Okay? So it's really these two things. Either I have a shear flow or I have an elongation. So if I look how the streamlines look like in an elongational flow, we would typically describe this as a stagnation point flow. So a stagnation point flow is something where actually fluid comes in from two directions. So here it's drawn in 2D and it actually goes on from the two others. So this is actually the same thing that happens in the filament. So if you stretch the filament, you will actually, it's like if you stretch in this direction, like if you bring fluid out here and fluid comes in from the side, okay? And the stagnation point, so what you need to know is that when the fluid comes in here, it will actually decelerate until a point here where the velocity is 0, and then will accelerate again. So while you decelerate, you will actually compress your fluid elements, and while you go out here, you will actually stretch your fluid elements. Okay, and if you write this in a more mathematical form, you can actually say that your velocity field is along the x-axis, and I hope I drew the arrows in the right direction. Along the x-axis, yeah, I think it's fine. You go from 0 velocity at the stagnation point to an linearly increased velocity when you go out, and on the y-axis is the opposite. And what we define now for the shear gradients in the system is actually called often epsilon dot, is dvx over dx. Okay? And just by construction, well, maybe there's some point I should say, we defined epsilon dot x in one direction, and this in 2D already defines what needs to happen in y. Because we are in a situation where things are incompressible, so what goes in one direction needs to go out in the other direction. So if now from this planar extension of flow I want to go to a 3D flow, actually it means that what goes into x will go out into y and z. So I get these two 1/2s. And this is exactly what we said. So actually this comes from incompressibility, and the sum of these terms, actually the trace is 0. Okay. So these are the two fundamental flows that we will deal with, the shear flow and the elongational flows. So now let's see what are the stress elements that we need to expect in these flows. And so people have constructed these flows because they have certain symmetries. And as we know that they have certain symmetries, these symmetries will also translate in some way to the stress tensor. So our stress tensor will be less complicated than if I would work in any kind of flows. So let's just have a look what they are. So in the simple shear, we can actually show that for any type of fluid, so I don't know anything about the fluid yet, but these two, of course, we know. These two are these tangential stresses that we already saw, but we also see that we can actually have elements on the diagonal, and now these elements are not the pressure. Okay? So these elements come from the interaction of the constituents of the fluid with the flow. So now there's more things that we can actually measure. So I still have a shear stress, will give some kind of viscosity, but I have also what we call these first and second normal stress differences. So the normal stress differences are always a little bit complicated to imagine what they really are, and I will spend some time on that later on. But you had a very nice discussion already by Frédéric, which kind of told you if you want to see an effect of these diagonal elements, they need to differ. If these diagonal elements are all the same, then you just have a static pressure, and the static pressure will never have any influence on movement. They will just compress the fluid from all sides. So this is why we say that what we can measure are the differences between those, and there's a definition of the first normal stress difference and the second normal stress difference. And I think that's what I put here. So we have a non-Newtonian viscosity, we have normal stress differences, and what is different for this non-Newtonian viscosity compared to the viscosity you had before is that it can now actually depend on the shear rate, so it will not be a constant anymore. Yeah. So here they are not coming from the pressure, not from the hydrostatic pressure. So I did not write the pressure part. So here they are viscous contributions. Okay. So it's really only the viscous stress tensor. Sorry? They can exist. Yeah. So for the moment we only know that they can exist. Or they are not forbidden by symmetry. And so if I talk about a simple elongation, the only terms I can have are actually terms on the diagonal. And so that always also leads to a first normal stress difference, but it was actually here is equivalent to a viscosity, an extensional viscosity. And that is what is written here. Okay. So for the moment, it's only a definition. So let's look in a bit of detail. How can I measure these things and how do they look like? So let's start with something relatively simple. So let's start just with non-Newtonian viscosity, and you will recover many things you've already seen, I think, during this week. So I want to start with a certain example, which is actually a polymer which is called xanthane, which is a rigid polymer. I copied that. I'm not a chemist. I hope it's the correct formula. I'm happy to hear more about that. But actually the xanthane is like a small rod. So it has actually a helicoidal structure that gives it stiffness. So you can imagine this to be a tiny Brownian rod. And its length, it's actually about a micron. And it has a quite high molecular weight. So if I put this polymer now in water as a solution and I actually perform rheology on it. So there's a number of things we can comment. So well, first of all, this is the shear viscosity, and I performed this actually in a classical rheometer. Well, I can, let me just see what we see, and then I comment on that. The concentrations are actually measured in ppm. So ppm are parts per million. So 1000 ppm, which is the highest concentration here, is 1 gram per liter. So it's still a very small concentration. So you put 1 gram of xanthane in 1 liter of water, and you get an increase of viscosity from 1, which is the viscosity of water, to 400. So it's enormous. So that's the first thing we should remark. And then, of course, this increase is proportional to some extent to the concentration. And we also see that we have actually quite strong shear thinning, and that you saw that nicely on a curve already this morning. And actually, in our case, we have quite a hard time to reach the second plateau that you saw this morning that actually occurs at very high shear rates. So the comment I wanted to make about the rheology is there's actually a regime which is really hard for a rheometer, is not two viscous solutions and very small shear rates. So that's here, because in this regime, actually the torques or the stresses that you create are very small, so you're very much limited by the resolution of your apparatus. So these points have been done with a specific rheometer, which is a low shear rheometer, which actually works with a torsion device to measure the stresses correctly. And then actually, I'm not completely sure, I think we actually worked with a quet and a cone plate. So we combined different types of geometries to be able to access different regimes and to get these kind of curves. So the fits that you see are actually done with this model. So this model is a model that actually takes into account the plateau, the N0 at small shear rate and the shear thinning, but not the plateau at high shear rate. But for most purposes of what I want to do in the following is that I will just use the simplest model possible, which is the power law. The power law just describes this shear thinning part. And you can actually see that it's mostly nicely followed for some parts of the situation. And so the power law for the viscosity is written as the shear rate to n-1, the power n-1. So you might wonder why this strange way of writing n-1. It's because if you write the stress would be actually linear in the shear rate, or the stress would be the shear rate to the power n. That's why it's written like that. So what we need to keep in mind is that for something shear thinning, n needs to be between 0 and 1. If it's 1, it's Newtonian. And if it's shear thickening, so it means that the viscosity will increase with shear rate, it's larger than 1. So, I mean, it's very nice to have these curves, but how can we understand these curves? So one thing maybe that you already realized that these non-Newtonian effects, here the shear thinning sets in at a certain critical shear rate, right? So we recover again the fact that if I would work only at very, very small shear rates, my fluid would be Newtonian. But what is this shear rate coefficient here, and how do these small rods that I put in the fluid actually behave with the fluid? And to do this, I need to make a small detour, and we need to talk again about the simple shear. So the simple shear has simple in its name, but is actually not a simple flow. So if you think about the simple shear, so what I did here is I actually described it in a way that indeed I have the bottom and top plate move, like it was shown this morning, and which means that in the midplane I actually have no movement. And then if I really want to know what happens in this flow, I need to take into account the asymmetric part and the symmetric part. So there's a rotation in the flow. I think intuitively we understand that. If you imagine you make a movement like that, you have a particle in there, it will actually rotate with the flow. So you have this rotation. And then this part is a little bit more difficult to see. We have a combination between a rotation and an elongation. But this elongation here is actually not along the x and y axis, but it's oriented at 45 degrees. So for those who have a little bit more mathematical background, if I go back here, I think here. So this type of flow we see is actually a matrix that is diagonal. Okay? Here this matrix is not diagonal, but it's symmetric, so we can make it diagonal. So what I can actually do is that I can look in what coordinate system would this matrix be diagonal. And it turns out that these are these 45-degree axes. So this corresponds to an elongational flow, but slightly turned. Okay? So a shear flow, and this is important to keep that in mind for all the rest. A shear flow is a combination between a rotation and a compression and elongation, but slightly turned. So now what happens if I put these elongated fibers in there? So the elongated fibers are not deformable, they're rigid. So probably the elongation will not do them a lot, but they will certainly feel the rotation. And that's actually what is called a Jeffrey orbit. It's a very specific movement that is known for very elongated fibers. So if you imagine you have your fiber in your shear flow, maybe you have a small fluctuation, then the shear will turn the fiber until it is again aligned with the streamlines. And then it will stay some time, and then it will do the same thing again. So if the fiber is very, very long, it will stay a very long time aligned with the shear flow and actually switch very quickly. If you think more like an ellipsoid, or even if you just take a sphere, let's just take the point of a sphere. So if I think I put a sphere in there, the sphere will just continuously rotate with the rotation rate of the flow, right? So I go between something that rotates continuously to something that will spend more and more time aligned with the flow. And that is actually what is represented here. Maybe it's the easiest to see here. So this is the angle as a function of time. So if my aspect ratio is only 2, so I'm just a slightly elongated ellipsoid, I actually spend a lot of time in the orbit. But already if I am at an aspect ratio of around 100, I will spend a lot of time aligned, and then I switch and I spend a lot of time aligned. Yeah. How do I get these curves? There's equations which are called the Jeffrey equation. And they come from the fluid-structure interaction of the rod and the fluid. And this is a solution of them. It's a very classical solution at small Reynolds number flows and fluid-structure interactions. But it's slightly evolved to get there. Yeah. So for the movement of the rotational, so okay, let me come back, because actually a very interesting question. So if I have a sphere, the sphere will not feel the elongational flow. So the sphere will only rotate at a constant rotation rate. If I get elongated, I will actually feel both. I feel the rotation and I also feel the elongational flow. And it's the combination of the two that will actually make the fiber rotate, not with a constant rotation rate, but it will have a quick orbit and then be aligned with the flow for a longer time. Okay. So it will not really stabilize a rigid object, but it will change the dynamics in which the object will rotate. But things will get very different if you put something that is deformable in there. Okay, so now if I have a fiber and I add nothing else, just a fiber that rotates, I now know that the fiber should spend quite some time aligned with the flow. So in this case, we imagine that the contribution to the viscosity should not be very big, because a fiber aligned with the flow shouldn't have such a big effect. But it turns out that actually I'm not having a big fiber, I have this tiny rod. So this tiny rod will actually be subject to Brownian noise. And that's actually really nice, because we heard about the Peckley number this morning also. However, what I'm looking at here is not the diffusion of the center of mass, but I'm looking at the diffusion of the orientation. Okay, so if I have a tiny Brownian rod, I do nothing to the rod, it will have random orientations and it will change between these random orientations. And this is actually given by something which is called the rotational diffusion coefficient. Okay? And then I can construct a Peckley number which will describe the interaction between the flow and the Brownian noise. Because the Brownian noise will try to have something where the orientations of the fiber are equally distributed. However, when I turn on the flow, the Jeffrey orbit term will want to overtake and wants to orient the fiber with the flow. And that's what you can see from a numerical simulation here. So actually the sphere represents the orientation of the fiber in the space. And where the color is higher is actually where the orientation is more likely. And we go from a small shear rate to a larger shear rate. And you can actually see that in average, things get more and more aligned. So, yeah. So actually, this is the direction of the flow. I guess this is the direction of the shear, and the vorticity should be out of plane. So yeah, so if you imagine that this is the flow direction, if I have Brownian noise, I can be oriented everywhere, and this actually gives the sphere. And then indeed, when I add on top of that these Jeffrey orbits, the Jeffrey does two things. It actually wants to bring it in this plane, but it also wants to bring it closer. I'm not sure my 3D hands are good enough. So without shear, it's equally distributed. And the Jeffrey orbit, because actually the Jeffrey here, I only show it in 2D, right? So here I'm only thinking about rotation in the plane. But of course, the fiber can also point out of the plane, the shear plane. Yeah, exactly. It rotates in the XY plane, and the Jeffrey orbit will do, first of all, bring the Y towards the X, but also the Z towards the X. And that's what you should be able to see here. So with this, we have actually found the time scale, which is the relevant time scale in this problem. So what actually the flow will compete with is, in this case, the Brownian noise, the Brownian rotational noise. And with this, we can actually explain this curve. And it's really nice because it's exactly the same shape of curve that you saw this morning, but the origin is actually different here of the shear thinning. Okay? But it's always interaction with the flow, but it's not the same type of alignment or interaction that you saw. So at very small shear rate, we have this Newtonian plateau. In this case, comes from the fact that there's no preferred orientation of your fiber, and we also see that the viscosity is very high. So the viscosity is very high because if the fiber has a random orientation, it's as if the fiber would occupy a really big space. So it's as if the fiber would occupy a space which is comparable to the sphere of the diameter of the fiber. And then I have this beginning of orientation, where actually we have this competition between reorientation and Brownian noise. And then at some stage you have the second Newtonian plateau, which is, as has been described this morning, it just means the fibers are all aligned. Once the fibers are all aligned, I can do nothing more to the system. And the shear thinning actually nicely sets in at something that is given by the Peckley number. Okay. Yeah. Yes. So I will come to the concentration dependence very soon. Thank you. It's true, I have not explained yet where indeed the value of this comes from. But before going there, okay, I think this we understand now. I want to make two detours. Actually, just for the pleasure, I want to show you another system that shows shear thinning, and then I'll come back to another polymer and answer your question. So I showed this because I told you that actually it would be really nice to be able to create this simple shear flow, but it's very hard to do this in an experiment. So, but some people did it. So that's actually a rheometer that has been built by Christian Claassen in the lab of Gareth McKinley some time ago. And that what they wanted to do is they wanted to perform rheology on spider silk. But one spider actually produces like 1 microliter of gland. So they needed to build a specific apparatus to do shear on this system. And it's actually not easy to see from here, but they have 2 parallel plates in here. They are aligned by interferometry. And then they actually have a step motor that will actually push one part to move. And here they have actually a deflection device that measures the deflection of this part. And you see all these complicated ways of actually building the 2 plates in how they are held together to be able to actually slide them in such a way that they remain parallel, but you can still impose a well-defined displacement and measure the stress. So yeah, it can be done, and actually it's still working in Christian Claassen's lab in Leuven at the moment, and it is specifically built to measure small, very small volumes. And with this, they actually measured the properties of the spider silk, and in shear you can see that they're actually very, very, very strongly shear thinning. So I'm not I'm not pretending that this is the same origin as what I just showed to you for the xanthane molecules, because here I'm certainly in a situation where I don't have a dilute system, and most things that get a little bit concentrated will orient in some way or the other under shear and will be shear thinning. So I have a question here and then there. Yeah. This? So here it should be taken more like a sketch. So actually I took this from a paper from David Santillon, where his main aim is to talk about viscosity of active matter. So I'm not completely sure, what it's normalized to. Yes. So no. So you should really not look at these numbers, and I also think this is only the polymer contribution. So if you want to look at numbers, we should look at these numbers. This, I would say, is probably dilute up to 250, yeah, for the xanthane molecules. It's not linear, yeah. Yeah, I agree. So here, if you would plot I think that's what you're saying, right? If you would plot the zero shear viscosity as a function of concentration, it's already not linear anymore. Is that what you? Mm-hmm. So without yes. I agree. So if to have shear thinning, you need to have a certain amount of N0 here. If not, you have nothing that you can shear thin to. but I don't completely agree about that. From a practical point of view, I agree with you that what I show here is probably not on a dilute regime anymore. But if you do simulations of the viscosity of Brownian rods, you can put as many as you want in the simulation without getting overlap, because you do them one by one, and you get shear thinning, which is actually what you see here. There's no. Well, what do you mean? There's no hydrodynamics? Yeah. So no. For me, there's a lot of hydrodynamics because they interact with the flow, which is what makes them aligned. Oh, no. Here in this picture, so in my xanthane solution, I completely agree with you, and it's maybe a bit of stretch for me to use them as I did, because here clearly, at least for those values, I'm already in a regime where I'm not dilute anymore. And the strong shear thinning doesn't come only from the orientation, but from interaction between different atoms. But you can get the shear thinning also in a regime. Yeah, in tumbling, yeah. So, but it actually really comes from the fact that you will orient things more and more if you increase your shear rate. Okay, well, we can continue this discussion afterwards. There was another question, yeah. To this? Yeah.
So my question is very stupid after 10 days of this talk. Because I've seen so many curves like this. My basic question is, I understand my point hits a plateau, but why is the plateau below and not above?
Oh, there's some situations where you can hit the plateau above, but most systems, and I think that's also what Rubinstein just said, in most systems you have things that will structure under flow in such a way that they will align or break or orient with the flow. So mostly everything, even this morning, the colloidal suspension, you saw at the end there was bands that were sliding amongst each other. So in nearly all situations, they will interact with the flow in such a way that will actually make the flow easier. So actually, I have one example a bit later about the shear thickening, but the shear thickening is much less general than the shear thinning. And maybe Vlasis wanted to talk about shear thickening, also about colloidal suspensions, and I have one example about shear thickening. Okay, more? Okay, so now a different type of polymer. So now I will talk about PO, which is a very flexible polymer. So contrary to xanthane, which actually for a similar molecular weight was a rod-like molecule, this will be actually a coiled molecule. And I think you've learned a lot about polymers in solvents. So we think about this polymer as a polymer that is in a coiled shape. So now if I actually do rheology measurements about this polymer, and again, I increase the concentration from 125 to about 1000, you can actually see that now the viscosity increase here is like, I don't know, maybe threefold or something like that. So it's much, much smaller. And now I need to be careful. So the dilute regime, actually, I think for this PO ends at like between 500 and 600 ppm. So indeed, these two are dilute, but the other two are maybe not dilute anymore. But we can see that the reaction is actually very, very different. So now actually comes the question, where comes the viscosity of this plateau? Okay. So for this, we can actually go back to this picture. So if I have a polymer that is in a coiled state, the radius of gyration or the hydrodynamic radius will be just the radius of the coil. However, if I think about these Brownian rods, they will actually occupy a volume that is comparable to a sphere occupied by this by its length. So you can already see that in an effective way, they will actually occupy much more volume. So I also wrote down here this Einstein viscosity. So first of all, you should probably be surprised that I write the Einstein viscosity here, because we've learned that Einstein viscosity is actually for hard spheres. So these are not really hard spheres. So first thing, to be able to apply this Einstein viscosity idea, which actually works rather well, we need to be in a very small shear rate regime. So the very small shear rate regime is actually like the plateau values here, which means that for the coil, I do not deform the coil, and it means for the fiber, I do not orient the fiber. Okay, so that's the first thing. And also, for it to work, I need to be in a regime where I'm very dilute, so that I do not have interaction between these particles. And that's, I think, the critique also that came on my curves. So if I now look at the values at very small shear rate here, as soon as I come to a regime where they will start to interact and I'm not fully dilute anymore, this simple picture that my viscosity will just increase with volume fraction will break down, and they will increase much more strongly, which is, by the way, a possibility to measure, and I think you've heard that a lot. It's this famous C star, a possibility to measure when I leave this dilute regime. So from this simple picture, we can actually understand that the flexible polymers will increase viscosity only very slightly, and that actually the rigid polymers will increase viscosity a lot. And this is also why they are called thickeners, and they lose a lot to add to fluids. And I cannot resist to make a small comment on the 2.5. So I want to make a comment on the 2.5 from a hydrodynamic point of view. Because actually the 2.5 for spheres can be deduced from the hydrodynamic interaction of a sphere with a flow. And without doing the calculations, because the calculations can actually be quite nasty, as more Reynolds numbers, if we go back to this, and I think you already had a feeling that something happens with the extensional flow, if I put a sphere in a shear flow, the shear will rotate, but all the time these elongational and compressive flow will actually pull on the sphere. So the flow would actually like the sphere to deform. But the sphere is not deformable, so the sphere will resist internally. And by doing this, the sphere will create a disturbance flow around the sphere, and this disturbance flow will create a stress on the flow. And this can be calculated. It's actually called a stresslet, and if you calculate the stresslet and you sum up the stresslet, you actually end up with this 2.5 value given here. So it's a term that really comes from the hydrodynamic interaction of a sphere with the flow, and is created by this extensional part of the flow. Okay, and now I come to something where actually the viscosity increases, and that's something I learned from Guylaine. So this is actually a polymer that is an associative polymer. And once again, I have to say I'm really not a specialist on these type of polymers, and you had very nice lectures about these associative polymers. But to be shear thickening, you need to create some kind of situation where something increases with shear. And I actually think that this is a very beautiful example. So what happens here is that actually above a certain shear rate, these associative polymers, or let's say below the certain shear rate, these associative polymers actually interact only within the same polymer. Then when you start to shear, you will start to open this coil, and then suddenly actually different polymer molecules will be able to interact with each other. And then very abruptly, the viscosity increases. Okay? So you can create a system in such a way that the reaction to flow increases indeed the viscosity. And the story I always tell, and Guylaine will tell me if after 10 years is still the correct story, is that it's actually something that has been developed to actually block holes, for example, for enhanced oil recovery. So if you imagine you have a system like that, you are in an oil well or another type of system, and you want actually to block small leaks that could happen on the side. If you reach a small orifice and you need to squeeze through the small orifice, you will strongly increase the shear rate. And so if you strongly increase the shear rate, you might actually block the small leak. And in this case, everything will go well. And I'm not completely sure if the story really goes like that. But one of the big problems you see here, that it works very nicely at small temperature, but it doesn't work anymore at higher temperature. If you think about an application in an oil well, these are probably not conditions that you can work with well. But as a system, I still think it's a really nice system. And other things that can lead to shear thickening are actually these shear thickening that you have in granular systems or in colloidal systems, which are often linked to some kind of jamming that is induced. And I hope you will hear more about that in another type of lecture. Okay, so this was everything I wanted to say about shear viscosities. You have more comments? Okay, so let's move to normal stress differences. So normal stress differences are actually much more difficult to handle and to understand than shear stresses. As we already said, first of all, it starts with the fact that you can only measure them if you have differences and also under certain conditions. And I want just to have a small reminder to what actually Frédéric told you, which I think was a very, very nice introduction. If you think about surface tension, if you think about surface tension along a straight line, you just have the tension along this line. But as soon as you curve things, this tension will actually lead to a force that is inwards. And it's this kind of force that you will be able to measure. Okay? So normal stress differences can, for example, be a tension along a line. So we can already intuitively think that probably we need curved streamlines to be able to measure them. Not always, but it's one way. So one way to do this, indeed, is just to go back to our cone plate rheometer. And now, instead of only measuring the torque, I will also measure the normal force. And if you look at the formula, we can have a result for the first normal stress difference, which is the force in the z direction divided by the surface. So it sounds really simple. And for a long time, I thought that normal stress differences mean I shear, I have a force in this direction. This actually happens when you walk on the beach, right? So if you walk on the beach, you have dilatation, you shear your granular or your sand, and the sand grains need to pass one over the other, so your system dilates. So you shear like this, you have a force in this direction. So I thought, great. Probably it's the same thing in the polymer solutions. It also really corresponds to this formula. But if you look carefully, there's this small 2. Not really clear where the small 2 comes from. And to tell you, for the polymer solution, this picture is really completely wrong. So to understand a bit better, so actually this small 2 comes from a very, very long calculation. So the first thing I wanted to show you is just one result, which comes from a very beautiful film. So the film is called Rheological Behavior of Fluids. It's on the MIT webpage. There's a whole bunch of films on hydrodynamics and different types of effects. So if you've not been there yet, have a look. So this film is also beautiful. It's very old-fashioned, but the experiments that are shown are really, really beautiful. And what is done here, I'm not sure if it's completely nice to see. It's actually a system where below you have a cone plate geometry. So the cone rotates, and what actually these small capillary tubes are filled with water, and the water will actually move up depending on the local pressure below. So what you see is that actually when you do your experiment and you want to measure these normal stresses, that the distribution of pressure below your plates is very complex. So if you look in detail, this is the formula that is given, but what we really see is this logarithmic dependence with the radius. So the situation already is much more complex than you might think. So on the next slide, I showed you the calculation. You can obviously not go through the calculation here. It's mainly to show you that the calculation is really complicated. I will cite the most important parts, and if you want to look at it later, you can. So from a mathematical point of view, I just wanted to tell you that this is the total force, and by miracle, if you integrate this total force over the surface of the plate, the only thing that is left is this prefactor, which I don't know, remember it's 1/4 or half or whatever. And so in the end, you end up with this very simple result for the force. But it comes from an integration of a really complicated distribution term. So where comes the measurement of the normal stress from is actually because you have these curved streamlines. If you imagine that you have a tension along the curved streamlines, this would actually push inwards. Okay? So this is still slightly simplified as a picture, but more or less it captures what you see. And then the next ingredient you need is that you have a boundary condition. So at the boundary, you actually connect to the atmospheric pressure, and that will actually create this overpressure in the middle. So it's very comparable to the rod climbing experiment. So you have the rod, you rotate the rod, it will move up along the rod. It's the same idea that you will actually push inwards due to this tension element. Yeah. No, now here I really draw it like that, but for simplicity reasons for the calculation. So not to take into account any surface tension effects. I think in reality it depends a lot on your material. If it's a little bit viscous and thick, you can squeeze it and you will have like a paste. You will have these, the surface tension like that. If it's very liquid-like, you will probably not have this boundary. So measuring normal stress differences of dilute polymer solutions on a rheometer is very, very difficult. Among other things, as your ratio between surface and volume is not favorable, so you have a lot of surface for not a lot of volume. So any kind of surface effects will play a huge role. And also, you in addition to the normal stresses, you also have the centrifugal forces. So you measure a combination of the two. Yeah. So it's hard to measure in reality. Okay, so normal stress differences can be measured. They are not easy to measure, and it's not always easy to understand exactly where they come from. But for these dilute polymer solutions, we can actually measure them. And I already showed you the viscosity as a function of shear rate, which, well, we have seen. Okay. Yeah, I will readjust my second part. So we saw that they don't have a lot of effect on the viscosity, but we can actually see that we can measure these normal stress differences. For these type of polymer solutions, these normal stress differences are always quadratic in the shear rate, so there's also quite some things behind that, but for the moment we can maybe just say that it's quadratic in shear rate. Something interesting to note is that when these effects exist, they're always important. So if I look, for example, at a shear rate of 1,000, I'm maybe at the stress of, I don't know, somewhere between 40 and 100 Pascal. And if I look at my viscosity, I have like millipascal seconds here. I have maybe stresses of 3 or 4. So when these effects exist, typically they are strong. Okay, but now where do they come from? So where do they come from? We need to go back to this. I think that's fully understood now. So let's see what deep type of polymers would do if I put them in a shear flow. So these are actually very, very pretty observations. So these are single molecule observations. I think now we take it for granted that obviously you can observe a single molecule under flow, but I think it was really, really a huge step forward, especially by the group of Stephen Chu, and this is also from their lab. So this was not their first observations, but I will show the first observations later also. So this is a DNA molecule. It's labeled fluorescently in such a way that you can indeed observe it in real time under a microscope. And they do the trick that we also saw this morning. So actually they shear, but in such a way that the shear plane that you want to observe does not move. So you can easily observe it under your microscope. And what they see is, well, I'm not sure if I should start here or there. What you can clearly see here is that you have a combination between stretching and recoiling, and you can also distinguish this tumbling motion. Okay? So what actually happens is that you put your polymer coil in the flow. It will be stretched along the direction of extension. It will be rotated until it reaches the flow direction. It will be rotated more until it reaches the compressive part. It will be coiled again and continues like that. So you have a continuous combination between stretching and recoiling, and tumbling of the polymer. Okay? And in average, if you want to know where the polymer spends the most time elongated, is actually along the flow line. Okay? So from this complicated tumbling rotation and tumbling motion, what we can keep in mind is that mostly the polymer will be stretched along the flow lines. And this is what creates this tension along the flow lines. It's like having a small spring that is stretched along the flow line, but this actually, the spring wants to come back, and this creates the tension. And that's what I tried to show on this sketch here. So I stretched them mostly along this line. And now actually it starts to make sense what this is, these normal stress differences. Because now I can look at the different contributions. I have sigma xx, sigma yy, and sigma zz. So I can actually see quite easily that the only one that most likely is non-zero will be sigma xx, because that's the direction I will actually stretch things at. And it's actually positive because it's a tension that wants to pull the polymer back. And the two others are 0. And then I can just construct my N1 and N2, and I see that N1 is bigger than 0 and N2 equals 0. Yeah. Yeah. No, it's certainly positive, but I think it's pulling back. It gives the whole system gets under tension. Yeah. I'm sure about the sign. It's a sigma for the fluid. So this gives us these normal stress differences which is larger than 0 or equal to 0, and actually they only make sense, these normal stress differences, if we actually know where these different contributions come from. So now we can imagine where N1 positive comes from, because it comes from the tension of these filaments along the lines. And maybe I will just quickly go into that. So I just wanted to comment quickly on that without going into a lot of detail. So I told you that for most of these complex fluids, we actually do not have a constitutive equation. But in some approximations, we can still do some modeling and build a constitutive equation. So many modelings actually of these kind of flexible polymers are done with a bead and dumbbell model. So you imagine you have two beads. The beads are actually transported by the flow and they are linked by a spring. And the spring actually represents the elasticity of the fluid when you stretch it. And then you can actually make statistical ensembles and you can actually try to model your system by using the interaction with those with the flow. And you end up with a model which is called the altered B or the second order fluid model, where actually you make the approximation of a Hookean spring, so you can stretch it as far as you want. It will always stay linear, which obviously is not correct for our polymers, and you have a single relaxation time. But I actually thought it would be nice to write them down, because I think what you can recognize in here, so the viscosity is the viscosity of the solvent and some contribution from the polymer, but you have N here, which is actually the number density, so the number per volume. So you can see that you have a signature of the concentration here. The more you put, the more actually you would increase the viscosity. And you can also recognize a relaxation time here. So for example, for this type of polymers, a relaxation time that works well is the Sim relaxation time. And you see that the Sim relaxation time has the radius to the power 3. So you can understand how the volume of each polymer comes in here. And for a larger relaxation time, you will have an increase in your viscosity, which is stronger. And the first normal stress difference are written like that. And you can actually see again that you have this quadratic dependence on the shear rate, which is actually made possible by the fact that you have this relaxation time to compensate that with. Okay, how much time is left? Okay, yeah, well, maybe I'll stop before I go to the elongation and take some questions. Maybe we've asked them all already.
Yeah.
Yeah.
If the coefficient of diffusion of alignment of the fibers
Yes.
is really low,
Mm-hmm.
would you see some sort of transient behavior in the flow?
Mm-hmm. Yeah, so if the coefficient of diffusion is really slow, you would be in the limit of a non-Brownian suspension. So you would be in the limit here. So everything I presented, and it's true I didn't really say it, is a steady state picture. But certainly if you would start your flow, you would see some transient where things would start to align with flow. But very big fibers would be actually in this limit, where once you have established your flow, it will not depend on shear rate anymore. Yeah. Yeah.
What about normal pulses in oscillatory shear?
So,
Because I would expect that, as you said, it depends mainly on the speed or continuous shear.
yeah.
But in oscillatory shear, I would expect it's more due to the strain rather than the shear rate.
So typically the oscillatory shear is really a picture of linear rheology and not of nonlinear rheology. The picture of the normal stress differences is really a nonlinear property where you are at a Weisenberg number which is bigger than 1, and when you actually induce large deformations to your system. Then oscillatory shear, you can also make longer deformations and things. So I don't know who has measured that exactly, and if in Laos people have measured normal stress differences, maybe somebody knows. But I know that for the fiber suspensions, it can be really interesting because you can lock into very different orientation modes, especially if you can start to deform things. But I'm actually not sure if somebody probably measured that. Yeah. But normally these oscillatory measurements are really a different type of regime. So for these very dilute solutions, if you measure classical G prime T double prime, you won't have the resolution to see something because you would just deform very, very slightly your polymer, for example, so you actually don't have any signal. So it's really a non-Newtonian, nonlinear property. Yeah. Should I?
Throw and back throw.
Okay.
If you want to touch on this a bit, I've seen the slide again and remind you. Does this effect go away when we increase the concentration?
So when we increase the concentration, the effect would get stronger, but would not really have the same origin. Because if you increase the concentration, fibers would actually influence each other. And they would still be oriented by the flow, but your Brownian diffusion would already be hindered in the beginning. So the time scale, I guess, would not be the same time scale as the times are given by the Peclet number. Yeah.
Maybe my simple view might go towards the liquid crystal.
So if you go to the idea of a liquid crystal, which really has given directions depending on the director, then even if you are not shear thinning in the viscosity, you have different viscosities depending on the direction that you're looking at. Yeah, so the situation is indeed still more complicated because by definition your viscosity will be anisotropic. Yeah, yeah. Yeah.
Could you go back to the slide with the polymer that's under the flow that
The experimental result? Or my sketch?
far along?
This?
Right there.
This or that?
So if you kept shearing this, does the molecule
Yeah.
stay in some I don't know if you said this, but does it stay in some like enclosing volume that is constant, or does it rotate even like a temporary particle?
Yeah. So this is really just a sketch, and here I'm drawing the most likely orientation of the stretched molecule. But you should really think about it like this. So if you're more or less coiled, you will be stretched in the direction of the elongation, then you're like a rod, and then you would turn with the flow, and actually you would rotate towards the compressive quadrant. You would even relax before. You would start relaxing, then you rotate to the compressive quadrant. You would be compressed, and then you would be stretched again. So it's really a loop that continues between stretching, tumbling, coiling, stretching, tumbling, coiling. It continues. It's just that most of the time the elongated filament is actually aligned with the flow, and while it's just a coil in the coiled state, it has much less influence on the flow. That's why, as an explanation with your hands, you can actually think about it like something that is stretched along the streamline. Even if it doesn't make sense to say stretched along the streamline, because there's no stretching happening along the streamline. Yeah. Yeah.
What is the effect of the fact that you have elongation in the terminals and microscopic processes?
So the effect that you have these stretching and tumbling is that in the end, and I will give an answer to a question I wanted to ask next time, is much less efficient to unravel polymers than an elongational flow would be. Because you only manage to extend a little bit and then you compress again, you extend a little bit and then you compress again. So I'm not sure, are you talking about the viscosity curve or the normal stress or? So basically what we measure here is probably something like an average extension I can reach for a certain shear rate. It's just that this average extension is significantly smaller in a shear. So imagine you compare, I don't know where this is. So imagine you compare an elongation alone of the same strength and an elongation in a shear flow. Okay? So the pure elongation would be much more efficient because it would just pull on the filament, whereas here it would always be stretched and coiled and stretched and coiled. Yeah.
So I think we have to stop here and go for a coffee or just to breathe a little bit. So thanks again, Anke.
Thank you.